We are going to talk about combining functions in various ways. So we're going to start with arithmetic combinations of functions. Those are just the four basic operations that we have: addition, subtraction, multiplication, and division. So if you have two functions f and g and they have overlapping domains, this is important because if you combine them, you need it to be defined for some values of x. You need overlapping domains. Then for that overlap, for the x common to both domains, then we define the sum, difference, product, and quotient in these ways. Okay, f plus g of x is simply f of x plus g of x, exactly what we would expect, right? If you add two functions, that just means add the two outputs for the given input. Same thing for subtraction, multiplication, and division. The one key thing with division is to remember that you're going to actually have to cut out some values of x sometimes because we can't divide by 0. So we cannot have g of x equal to 0. So that may add an extra restriction to your domain. Let's go ahead and look at some examples. So we've got here two functions, f of x equals 2x plus 1, and g of x equals x squared plus 2x plus 1. For part A, we'd like to find f plus g of x, and then f plus g of 3. So for f plus g of x, we know that our definition is simply f of x plus g of x. Okay, so that's equal to 2x plus 1 plus x squared plus 2x plus 1. Now, we can, of course, combine some like terms here. So we've got this 2x and this 2x that can combine. Okay, so we've got our x squared, and then we combine those two x's, and that's 4x. And then we also have this one and this one that can combine, and that's plus 2. So there's our combined function f plus g of x. And then we can find our f plus g of 3. And we could do that in two ways. We could plug it in both f and g and then add, or we could just plug it into this function here. And I'm going to go ahead and just plug it into this function here. We've got 3 squared plus 4 times 3 plus 2, which is 9 plus 12 plus 2, and that's 23. Now we want f minus g of 2. All right, let's go ahead and find f minus g of x. F minus g of x, we just simply subtract those two functions. Now with subtraction, you want to be careful because we're subtracting the entire g of x. So I'm going to put that in parentheses because that negative is going to have to distribute across all of those terms. And so we end up with our 2x plus 1 and then minus x squared minus 2x and minus 1. And now notice that the 2x cancels because it's 2x minus 2x, and the 1 cancels. Okay? We are just left with negative x squared. So now for f minus g of 2, well, that's negative 2 squared. So we do our 2 squared, which is 4, and we have a negative in front of that, so we get negative 4. And now for part C, we want to find f over g of x and state its domain. So that's f of x over g of x. So that's 2x plus 1 over x squared plus 2x plus 1. And we want to find its domain, and we know that the domain of both of these functions is all real numbers. Okay, there's no restrictions here. However, here we are dividing, and so our restriction is that x squared plus 2x plus 1 cannot equal 0. So we need to find the zeros of this function here. We can factor this. This is x plus 1 squared, actually. And, well, if that can't equal 0, then x plus 1 certainly can't equal 0. And then we can subtract 1 from both sides here to get that x cannot equal negative 1. And so our domain for this function, if we write this in interval notation, is negative infinity to negative 1, and then union negative 1 to infinity. Now, those arithmetic combinations of functions are very straightforward, right? We'd add, subtract, multiply, and divide. It's not too difficult. The next way we're going to talk about that's a little bit more involved is composition of functions. And this is where we use one function as the input for another function, okay? So this is how we notate it. The composition of the function f with the function g is, and then we've got this notation here, okay? F, and this little circle here we would just read as composed with. So f composed with g. of x, and that by definition is simply f of g of x. Notice that g of x here is the input to the function f. Okay. The domain of this function, the domain of f composed with g, is the set of all x in the domain of g. We have to be able to plug them into g, all right, such that g of x is in the domain of f. So there's two things to check here. Number one, you need to be able to plug your thing into g, into the function g. So your domain for the composition will be a subset of the domain of g. But then we also have to make sure that whatever g spits out for that input is in the domain of f. Okay. I like to just draw a diagram for composition of functions. So let's say this thing here is this is the domain of g. Domain of g. Okay, and over here is we're going to call this the range of g. And so we've got our function g that takes some x here and sends it to some g of x here, all right? So the range of g, we hit everything in here. But we also have a function f, all right? And the function f is going to take points and send them somewhere. I'm going to go and call this the range of f, all right? Now, the domain of f will overlap, hopefully, with the range of g. Okay, so I'm going to go ahead and draw that like this. This is going to be the domain of f. Okay, and the things here we send across. Now I'm going to go and take this g of x. Notice that this g of x I've drawn it so that it's in the domain of f. So we could take that and send it over here, and this here is f of g of x, okay? So notice that our domain of g may go to everything here, but some things in the range of g are not in the domain of f, okay? So that means that whatever gets sent to this portion over here, and I'll highlight that here in red, okay? This right here may be sent to by some portion of the domain here, okay? And that portion right there, that's not going to be in the domain of f composed with g, okay? And then there's another portion of this, okay, that would be sent. Oh, I'm sorry, that's not at all what I wanted to draw. There's this portion right here, okay, that we don't actually even hit with our g. And so that is going to be over here. The range of f is not necessarily the range of f composed with g. All right. Now, that's just a kind of a visual to kind of get an idea of what's going on here. Actually, finding the domain of our composite function is not too difficult. We'll be able to do that algebraically. So here's an example with two functions, f of x and g of x. F of x equals x plus 2 and g of x equals 4 minus x squared. We'd here like to find f composed with g of x. So by definition, that is, let's change out of blue. This is f of g of x. So I'm going to do this kind of from the inside out. So g of x is 4 minus x squared. So I'm looking at f of 4 minus x squared. Now this input here is going to be the input to our x for our function f. Okay, and so we get that thing, 4 minus x squared, that's the x, and then plus 2. Okay, and then of course we can just simplify by combining these two things. Okay, and that's 6 minus x squared. Okay, let's go ahead and look at g composed with f. That is g of f of x. So starting from the inside out, I've got g of f of x is x plus 2. Okay, and then, well, x plus 2, we need to plug into the function g. So that is going to be, so I've got this input right here, and that goes right there, that x. So I get 4 minus, and then x plus 2 is the thing being squared. So x plus 2, and notice I put it in parentheses because that squared has to happen to the whole thing. Now this is not simplified, so let's go ahead and simplify it. We've got 4 minus X plus 2 squared, we need to FOIL that. Okay, that's x squared plus 4x plus 4. Now this negative we can distribute. We have 4 minus x squared minus 4x minus 4. And then we can cancel this 4 and that minus 4. And we're left with simply a negative x squared minus 4x. Okay, and then we want g composed with g of x. So that is g of x. Okay, this is going to be kind of fun to do. So the inside, we have g of x is 4 minus x squared. Okay, now this input there, that is the input for g. That's going to go into that x right there. So we have 4 minus that thing, 4 minus x squared, squared. And again, we gotta simplify this. It's not simplified. So we've got 4 minus, and then this is going to be FOILed. Okay, I'm going to go and write that one out so that we can see it. It's a little bit, maybe it looks a little bit more complicated than what you're used to. Okay, so that's what we're kind of looking at. So we've got the 4 times 4, which is 16, and then 4 times negative x squared is negative 4x squared, and then negative x squared times 4 is negative 4x squared again, and then negative x squared times negative x squared is positive x to the 4th. Now, let's go ahead and I'm first going to just combine my like terms, these two middle terms there, minus 8x squared plus x to the 4th. And now distribute the negative. So minus 16 plus 8x squared minus x to the 4th. And now the 4 minus 16 combines to be a negative 12. And there's our simplified g composed with g of x. Okay, here's an example that's a little bit more involved, and we're going to find the domain. Okay, we want the domain of f composed with g for f of x equals x squared minus 9, and g of x equals the square root of 9 minus x squared. So the first thing you're going to want to do for this is simply find the domain of g, because you know that your domain cannot be bigger than the domain of g. So looking at g of x, we've got g of x equals the square root of 9 minus x squared. Well, we're taking a square root here, and we know that whatever you're doing a square root of has to be greater than or equal to 0. Okay, so if we add the x squared over, we get 9 is greater than or equal to x squared. Okay, so for this, when we take a square root, we actually get both sides. We get the 3, but then on the other side, we get a negative 3. Okay, so that right there is our domain for g. Writing that in interval notation, we've got brackets around negative 3 to 3. Okay, now for f composed with g, we just need to make sure that the output g of x is in the domain of f. Now the domain of f is all real numbers because it's x squared minus 9. There's no problems there. So automatically we know that this domain, negative 3 to 3, is contained within there, and so that's going to be the domain for f composed with g. Domain of f composed with g is that entire interval. Now I'm going to go ahead and find this function f composed with g so that you can see something interesting that happens. I'm going to go ahead and do it right here. F composed with g is f of g of x. So g of x is the square root of 9 minus x squared. Now if I take that and plug it into my f function, I've got x squared, so I have that input squared, and then I'm subtracting 9. Now I can simplify this. Okay, 9 minus x squared, I have to give the square root of that, but then square it. And the square and the square root will cancel each other out. Okay. Now there's actually an issue here, and the issue is that this looks like it has a domain of all real numbers. It doesn't look like there's any issues here. Okay, but this came from a square root of something, okay? And so that's why finding this domain first is actually pretty important, okay? Now we can simplify one more. We've got 9 minus 9. Those cancel. We simply get negative x squared. Okay, So the composition of this function, this composition f composed with g, even though it simplifies to negative x squared, we actually only have the portion of this function from negative 3 to 3 for our x values. Now, another thing that we need to be comfortable with, which is essential later on in mathematics, especially in calculus, is being able to look at a function and view it as a composition of two other functions, okay, and break it up into that in that way. So we're going to take this function h of x and write it as a composition of two functions. So what we want to do is we're simply saying I want to write h of x as some f of g of x, okay? And what we want to do then is say, well, and there's multiple ways to do this, okay? There's not going to be one right answer, okay? G of x, we want g to be the thing that happens to x first. So looking at this function, okay, if we were to, like, say, plug a value in for x and try and evaluate this, the first thing we would do to x is subtract 2. So what we can do is say, well, g of x is just, I'm just going to say that's equal to x minus 2. Okay. Then the question is, what is happening to x minus 2? And that's going to be f. All right, so f of x equals, and now look at what's happening to x minus 2. Okay, we're squaring it. So f is going to take our input and square it, but then it's 1 over that. So 1 over that. Okay. So this is a possibility. This is one way that we could write two functions where this h of x is the composition of those two functions. Now that's not the only option. Okay, let me just show you one other. We could have said let g of x be the x minus 2, but let's go ahead and square it. Okay, and then the only thing left to do would be do 1 over that thing, so 1 over our input. Okay. So these are two options, and there's not one of them is correct. Not one of them is the right answer. They're just both correct answers, and you could do either one. It's totally fine, all right? And in fact, you could even go further and say, well, I'm going to view this as a composition of 3 functions, because there's 3 things happening here, right? We're subtracting 2, and then we're squaring, and then we're doing 1 over that. Okay, so there's 3 things happening, so you could even view it as a composition of 3 functions. Okay. Let's look at an example of a composition of functions here. So here we've got the number n of bacteria in a refrigerated food is given by this formula. N of t, where t is temperature, equals 20t squared minus 80t plus 500. Okay, and here we've got a domain of t ranging from 2 to 14. Okay, so when our temperature is between 2 and 14 degrees Celsius. When the food's removed from refrigeration, the temperature of the food is given by this. Okay, our temperature at time t is equal to 4t plus 2. And here our time ranges from 0 to 3. Let's go ahead and find and interpret n composed with t, capital T, of t. So this is n of t. So this is n of 4t plus 2. And now we take that and we use that as the input for our n. Okay, so that's going to come in, and that's going to be every t that we see is going to be that 4t plus 2. All right, so we've got 20 times 4t plus 2 squared minus 80 times 4t plus 2 plus 500. Okay, and now we need to make sure that our domain is all lined up. Okay, notice that when t is 0, we get 2 for capital T, so that works out. That ranges up to 3, and when we plug in 3 here, we get 4 times 3, which is 12, plus 2, which is 14. That works out as well, all right? So our domain is still this entire 0, 2, 3. So there's our composition of functions. We could go ahead and multiply all this out and combine some like terms to write a simplified form. I'm not going to worry about that right now because I trust that you can multiply things out. It takes a little bit of time, but it's not too bad. So there's our function. We want to interpret this. Well, the output of the last thing we did here was n. Okay, so this is the number of bacteria. So this is the number of bacteria in the food, after time t, All right. Finally, find the time when the bacteria count reaches 2,000. So we actually are going to have to multiply this out. Let's go ahead and do that. So we've got 2,000. We want the number to equal 2,000. Equals all of this. Okay. Oops, that's not. So 20 times. Let's go ahead and multiply this out. That's 16t squared plus 16t plus 4 minus, let's go ahead and distribute that, 80, 320t minus 160, and then plus the 500. Okay. We can distribute the 20 through, so we get 320t squared plus 320t plus 80, and then minus the 320t minus the 160 plus the 500 equals the 2,000. Okay, our 320t cancels here. That's very nice. Okay, so now let's go ahead and then we've got these constants here. We've got 80 minus 160. That's negative 80 plus 500 is 420. Okay, so we get here 320t squared plus 420 equals 2,000. Okay, and we can keep going here. Let's go ahead and subtract 420 from both sides. And we get 1,580 equals 320 t squared. And now we divide both sides by 320. So let's see, 1580 divided by 320 equals t squared. I can't do that in my head, and we could do it by hand, but I'm going to go ahead and jump to our calculator and do that. So 1580 and divide that by 320. Okay, we get this this fraction here, and I'm going to go ahead and just take the square root of that. So take the square root of both sides, and t is going to equal. And remember that, of course, every time you do a square root, you get a plus or minus. But we know our domain for t is between 0 and 3, so we're not going to have any negatives. So I only need the positive square root. So square root of the 79 over 16. And let's go ahead and do that here. So take the square root of that 79 over 16. I'm going to go ahead and hit Control Enter to give me a decimal. And I'll round that to 2 decimal places, 2.22. Okay, so there's our time when our bacteria count reaches the 2,000.